It's a pleasure to be here, and I want to thank the committee for inviting me to give this keynote at USENIX. I actually wanted to say that even when I was at the National Science Foundation, I started talking about cyber-physical systems. I started a program in cyber-physical systems while I was at NSF almost 10 years ago. And even then, I started talking about the security challenges that cyber-physical systems are going to pose. And so I now can really talk about CyberTrust, including security, because now cyber-physical systems are real, and they're really affecting our daily lives. So with that, we already have thermostats and light bulbs that are smart enough to go on and off. We have robots that clean our carpeting and our floors. We have cameras that monitor our babies when we're at work. And we have devices that we can just, gesture over that are going to control and monitor these cyber-physical systems, these smart devices. We have cars that drive themselves around on the streets. Drones that fly around delivering packages or going into areas that we can't go into. Contact lenses that continuously monitor our glucose level and tell our doctors how we're doing. And sensors and actuators in our environment, our physical environment, our buildings, farmlands, all of these are examples of cyber-physical systems. Robots will be our pets, our coworkers, our companions, and help us in the clinics. And we have already invented devices that help the people who have disabilities to do things that they cannot currently do. So all of these devices are going to be, the promise of Internet of Things or the industrial Internet. All of these devices will be interconnected. They'll be, in principle, talking to each other, cooperating with each other, and so on. And also there's the cloud, which is another big component of this interconnected world. So what is common to these cyber-physical systems? They have a computational core that interacts with the physical world. So that's why I call them cyber-physical. Cyber-physical systems are engineered systems that require tight conjoining of and coordination between the computational, discrete, and the physical, continuous. And the trends that I see for the future are already happening. Cyber-physical systems will be smarter and smarter. All this smarts, this intelligence will be in software, and there'll be more and more connectivity and flows among these devices. And another important trend that we mustn't forget is that in the end, humans are going to be very much a part of this system. So we're going to have to understand how humans interact with these devices, and they are part of course, the whole ecosystem. So it's not just individual human behavior that we need to understand, but it's the social norms as more and more of these devices become part of our daily lives. So what could go wrong? This is a security conference, so we always worry about what's going to go wrong. And first, of course, things can fail. So planes crash, cars crash, trains crash, and drones crash. We've seen lots and lots of examples of this. And as these systems become smarter and smarter, software will be pointed to as often the culprit. Security errors, I don't also have to belabor with this audience. We see the headlines every day on how vulnerable a lot of these systems are individually, let alone as an interconnected system. So what I like to think about when I think about CyberTrust for cyber-physical systems is first, of course, there's the hardware, the software, and the people. I already argued that it's a big ecosystem, and the hardware and software interact very closely. But when I talk about CyberTrust, I mean not just security, I mean reliability, security, and privacy. So in the remaining part of my talk, what I'm going to do is outline research challenges, because this is a research community, and I hope there are a lot of PhD students in the audience looking for thesis topics, because there are a lot of really hard challenges left in order to make these cyber-physical systems trustworthy. And in the end, if these are part of our daily lives, we want people, you and me, our friends and family, to trust these systems. So I'm going to go through research challenges along the lines of reliability, security, and privacy. And some of the examples I'm going to give are historical, because we've come a long way. Some of them are very current, and examples of some research projects going on at Microsoft, for instance, that are addressing some of these challenges. So it's a mix of what we know how to do and what we're doing today and what we don't know how to do. Okay, so let's start with reliability. If you think about inherently a system that has a physical component and a digital component, and this device is interacting with the real world, then there are fundamentally two technical challenges we need to address. First is reasoning about the continuous and the discrete at the same time. And the second is reasoning about uncertainty, because the environment is unpredictable. And uncertainty can come due to Mother Nature, due to malicious attackers, and just due to failures of the components. So let me talk first about the fact we've come a long way in reasoning about the continuous and discrete at the same time, but there's still a lot of interesting new work being done. And then I'll talk a bit about reasoning about uncertainty. So let's dial back a couple of decades already to models for cyber-physical systems. And these models stem all the way back to certain kinds of automata. In this particular case, I'm highlighting Tom Hensinger's work on hybrid automata. And this is a simple model of a thermostat. And what's interesting about these automata is that within a state, you can describe continuous behavior, usually using differential equations and so on. And then between states, you can define these jump conditions that get you from one state to the other in terms of these discrete behaviors. Like in this case, the heater is going to go on as soon as the temperature falls below 19 degrees. And you can even state invariance. In this case, for this particular state, you can say that at the latest, the thermostat will go on when the temperature falls to 18 degrees. And so you can build these, you can define and build these hybrid automata to describe the behavior, both discrete and continuous, of these cyber-physical systems. So, and since then, many tools and other similar models have been invented in order to formally reason about these cyber-physical systems, or models of these cyber-physical systems. So this is tremendous progress by the formal methods community. There's another view on how to reason about the continuous and discrete at the same time that isn't so model-based, but in fact logic-based. And here I'm going to highlight the work of Andre Plotzer at Carnegie Mellon on differential dynamic logic, which in one logic allows you to reason about both discrete and continuous. So you can see in there's a, I don't expect you to see all the details here, but there's a way in which you can write a program that describes the behavior of a cyber-physical system, and that program has both differentials like x prime equals, for instance, predicates like q, which are over discrete variables. And then you can reason, much like we do in other kinds of temporal logics, we can reason about all behaviors, there exists behavior, etc. And this particular differential dynamic logic also has a tool that has been used to reason about air traffic control, about cars entering roads, and keeping trains a certain distance away. So this logic and this tool have been used to reason about cyber-physical systems. So again, tremendous progress in this area to reason about the continuous and discrete. So what about reasoning about uncertainty? In the past, typically in the formal methods community, we would model uncertainty by non-determinism. This is a very blunt instrument where you'd say, well, at any particular state, you can go into a failure state, which is, okay, it models what can happen, but it's not very satisfying because at any particular state, you can go into the failure state. And so you have to always think about that. So more recently, people have been using probabilities and inventing automata, model checking, theorem proving, logics, and so on to incorporate probabilities as first class in reasoning systems. And I think what's most exciting in this realm of adding probabilities is this whole era now that's starting on probabilistic programming. And here we have program variables, for instance, C1 and C2 here, that range over probability distributions. So you can actually choose a value for that variable that comes from a probability distribution. Now imagine programming in, say, a C language here, where your program variables are coming from probability distributions. This is a whole new way of thinking, a whole new way of programming. And for those of you who are faculty in the audience, a whole way of teaching your students how to program for the future. So this is quite far out, but we have, of course, already in the research community been inventing these probabilistic programming languages and reasoning about programs in these languages. So with that, I wanted to explain a little bit of work that is going on in a project at Microsoft Research called Safe Cyber-Physical Systems. And the project's underlying platform is a drone, or drones in general. And what they want to do is actually reason about the safety of a drone flying a particular plan from the bottom up. So they we're looking at this as a layer of abstractions. At the very lowest, we have an operating system, and in this particular case, it's a real-time operating system which we've proven secure with respect to memory safety properties. And then you have, on the drone, of course, you have many sensors, including cameras, which need to be proven robust because sensors can get imprecise data, in incomplete data, can make mistakes, and so on. And then, of course, at the heart of this is correct control. You want this drone to fly in a smooth, continuous path from a source to destination. And at the highest level, this drone or this cyber-physical system is supposed to do something interesting. For instance, carry a package or go region. And so there's high-level planning that takes place at the highest level of what the drone is supposed to do, the task. And so we have lots and lots of expertise at Microsoft Research in terms of verification at each of these levels. What I'm going to focus on is new work that looks at how we have incorporated Bayesian classification into a kind of temporal logic in order for us to reason about correct control. In particular, if you want to reason about safe control under uncertainty, you have your standard set of equations that define the next state of the system under some control variable. U is the control variable there. And you want to basically optimize the control to minimize the cost on where you want to be and the cost on control. And basically minimizing this expression. So the first part of this under the minimization is the reference, where you are to where you want to be, and the U's represent your control variables. But this is the standard optimization for control. What's different is we want to subject this constraint to a safety property. So if X is basically, think about what X represents your state, U represents your control variable, you have a sequence of X's and U's, you want each one of those sequences to satisfy a safety property. And in this case, we're going to write our safety property in what's probabilistic signal temporal logic. So that's just logic which one can reason over. Just to be an example of a drone that we are minimizing with respect to where we started, which is a 0, 0, 0, to where we want to be, which is 1, 1, 0. So this drone is this little green thing that's flying upwards to get to its destination point, 1, 1, 0. But of course, we don't want it to crash into the ceiling. And so the tech person is here signaling me something. Take it out. Okay, so here we're, as I said before, we're going to minimize the cost of where we are in our control subject to this particular safety property. And this particular safety property has two parts to it. One is just with respect to the control. There are actually multiple, but I'm just showing you the property with respect to role. But the interesting one is the first one, where we incorporate a Bayesian classifier to give us a confidence level of the probability that the drone is thinks it's near the wall or not. And so this is the new work here is really incorporating this Bayesian classifier in the logic itself. And then what you can do very beautifully is you can independently and modularly incorporate as many classifiers as you want and reason about them as compositionally. And the work I cite is in a couple slides before. I cited it. It just appeared this summer. Okay, but where we're going with this work is actually what, as I alluded to earlier, is that we'd like to actually write programs using the probabilities as part of our program variables, but also incorporate in these programs a check that basically checks these probabilistic formula. So what we have in the end is a probabilistic safety program, and the three inputs to this program are first some using planning and control. We have a trajectory, and then another input are the classifiers that are coming out of these Bayesian graphical models, for instance, for a camera. And then we have these specifications written, these logics. We fold them all into a program, and then we can basically run the program and do analysis of the program to determine whether we are guaranteed that every run of the program will be safe, or spit out an example where it's not. So this is, I would say, pretty state-of-the-art in terms of where we are in reasoning about uncertainty for cyber-physical systems. And that's all I'm going to say about reliability. Okay, now let me turn to security, which is probably of primary interest to all of you. And again, I don't have to remind you of the challenges that we have as a community to protect our systems and protect our networked systems. And in the future, or the way it looks today already, is there's some malicious guy out there, and this very highly interconnected network, including the cloud. Some other node in that network gets hacked, and the question is, what part of the system was vulnerable that caused this particular attack. In fact, many parts of the system are potentially vulnerable. How do you actually trace back and figure out what actually happened? So I divide this problem into three major challenges. One is, how can we protect each device from the network and the network from each device? This is like the atomic entity in this big Internet of Things, industrial internet, and so on. And then, of course, there's the network itself. How can we secure the network? And finally, there's the cloud, which is a part of where the interesting data, computation over data is happening. How can we trust the cloud? So all of these are big research areas on their own, but this picture puts it all together. So let me talk a little bit about each of these. So for the first one, we already, in principle, know how, in terms of best practices, to build a secure system from the hardware all the way up to applications. Device identity has to be in hardware. That allows us to do secure boot, which can then allow us to build some kind of secure storage. Then from there, we can build secure protocols and use encryption. And finally, we get applications running on top of that. Now, we know how to do this in principle for secure systems, but what about when the device is resource impoverished, like a thermostat or a light bulb? So what we need to do is revisit this security stack when the devices may not have the full capability, both in terms of storage and computation, as a typical system that we want to secure. And so this is where the research has to happen. And how do we build these devices and ensure and build the security stack for low power and limited computing resources? The other interesting challenge, not so much for the security community, but I would say for the software and machine learning community, is in the end, these devices are supposed to be smart. And so where's the smartness going to come from? Well, today, a lot of the smartness comes from the machine learning and the classifiers that we train using machine learning. And so now there's an interesting question of how do we split the machine learning models between the device and the cloud? Because we could have a really dumb device and then put all the smarts in the cloud. But then you have this latency problem, and you may even have privacy issues and so on. So you have to think, what part of this model or what part of the algorithm am I going to want to have local to the device versus have a compute in the cloud? So this is actually a project going on at Microsoft Research called Intelligent Devices, which is looking at machine learning algorithms and other kinds of algorithms to determine how to split that computation. So challenge number 2 is the something that we all care about, which is securing the network. And I know this afternoon you're going to have a keynote speaker who will address probably the Achilles heel of the network, which is HTTPS. So we have another project going on at Microsoft Research. I see Cedric's in the audience, smiling there, which is really quite ambitious. So first of all, I think everyone here knows that HTTPS is the workhorse of the internet in terms of it being the most widely deployed security protocol. And it is, of course, behind everything that we do whenever you go to the web, whenever you go to your browser, email, you name it. And it's quite complicated. It's not just one protocol, if you will. It's a bunch of protocols and components and languages and applications that talk to each other. And so the right-hand side is meant to be a box and line diagram of HTTPS. And it is also quite vulnerable, as you'll probably hear later this afternoon. 20 years of attacks and fixes, and we're still finding bugs, and we're still vulnerable to pretty severe heartbleed-like attacks. So the Microsoft research project called Everest has this grand ambition that in 4 years, what they hope to do is to build a fully verified drop-in replacement of the HTTPS ecosystem. So that whole box with all those complicated boxes and lines, they want to make green. They want to make completely secure. And the point about it being a drop-in replacement is that it should be performant enough and it should be easy enough for you to just switch over. Now, this is quite an ambitious project, but if we can pull this off, it's going to benefit the entire community, and we're quite excited about the potential. Now, this is a brand new project, so none of this has been done yet. However, they build on many, many lines of work that have already given us confidence that we could pull this one off. And it starts with some work on the Iron Star projects, Ironclad, Iron Fleet. Many of you probably have heard about this work through either Oakland or USENIX. And it also it builds on the phenomenal work on verifying a TLS protocol called MyTLS, which was also Oakland award-winning work. And then, of course, all of those projects, Ironclad, Iron Fleet, MyTLS, build on decades worth of verification tools and languages that have been invented a lot at Microsoft Research. For instance, Daphne and Boogie for specifying a pre- and post-condition-like specifications, F-star, which is a high-order functional programming language, Z3, which is the workhorse of almost all formal methods tools used globally, and so on. So we have high hope that we can build on what we've done already to achieve this grand goal. You should realize that what we can do already is just the little that is shown in green. So we do have a long way to go, and you should wish us luck. Okay, and these are citations from the previous work. Okay, so that's the network component. There's still one other component. Say we secure the devices, and we secure the network, but what about this cloud? Why and how can we trust the cloud? So I'm only going to speak a little bit about this. We all have some very, very exciting projects going on in Microsoft Research on building a trusted cloud. I'll just hint at a couple of approaches that we're taking. One is to, of course, use cryptography. I saw some opening advertisements for talks today and tomorrow on, for instance, using secure multi-party computation, but also using homomorphic encryption. So applied cryptography can go a long way in helping us trust the cloud, in particular trusting the data that customers and consumers will store in the cloud, and making sure that, for instance, cloud administrators can't see the data. But another approach is a hardware-based approach, and we're already seeing processors like Intel's SGX coming out with the ability to build what are called enclaves, regions within which you can run code over data in a secure manner. So it's as if you were computing over encrypted data, as you would in using, say, homomorphic encryption. So these are two approaches that the community is taking to build a trusted cloud. Now, at Microsoft, we actually already, in our Azure SQL Server, the latest release this year, already use a very baby version of homomorphic encryption just for one operation, essentially equality, to allow you to compute over certain columns in a relational database in a secure manner. So we're kind of using this as a stepping stone to see what we can do more generally, not just equality, but other operations. So that's all I'm going to say about security. Now let me turn to privacy. And I'll pull out this particular headline about how easy it is for people to hack these cameras that monitor babies, these baby cams. And again, headline after headline. And this is, of course, an invasion of privacy. So when I think about privacy, I think about the appropriate collection and processing of information about a data subject by a data holder and the flow of information between data holders. And appropriate is where we get all tangled up into what does privacy mean to you, to me, to a group of people, because that's where social norms, context, ethical values, company policies, legal rules, individual preferences come to make this notion of privacy so nuanced. So I'm going to just focus on what I call the data life cycle. We start with collecting data. We need to store and manage the data, and we analyze it and maybe share the data with others. We do the analysis to gain insights. We share the data with others to learn collaboratively and so on. And in this entire life cycle, there is usually a promise that a company might make to a customer to preserve certain policies, or the promise will be these privacy policies. And there is a question, of course, how can we trust the data holders with our data? So there are risks in the data lifecycle. First of all, there's very well known that anonymizing data when you're collecting it, it just doesn't work, so don't do that. And then there's a question of what I was alluding to before. You have this privacy policy, and how do you know that the company like Microsoft or Facebook or Google is actually complying by this promise that it makes to the customer with respect to privacy? And then I can tell you that certainly within Microsoft, that we're so afraid to violate customer privacy that we actually don't share with business groups within Microsoft because we prefer to err conservatively. And what this actually means is that we can't take as much advantage as we could if we were able to share data with each other. But at least we are upholding our promise to the customer. So in addressing each of these parts of the data life cycle, there are lots of different privacy technologies that can come to bear. And this is one thing that I'm trying to promote within Microsoft, and I hope as a community, when we think about the national issues of privacy, that for the most part, many people working in privacy have come from the policy, legal, ethical, even philosophical points of view. But as technologists, as computer scientists and engineers, we have a lot of technology to offer that can actually speak definitively about privacy. And so we shouldn't be afraid to actually use this technology and deploy this technology. And we are seeing companies starting to do that, so this is really heartening. One of the areas that my colleagues and my colleagues at Carnegie Mellon and at Microsoft Research and I have done, this is also an Oakland paper a couple years ago, was to how to actually abide by these privacy policies for large data systems, like large MapReduce-like systems. And we have the system, we wrote about it, and it's been operational. We run this tool nightly to check for violations of privacy policies. And it is scalable. It's basically, if you've got a large organization, it's something that you could definitely use. So we have we have hope that we know how to do this at scale. What about the collection of data? We know, as I was saying before, anonymization doesn't work, so what's the alternative? And here again, many of you, I'm sure, know about the groundbreaking work on differential privacy that also came out of Microsoft Research with Cynthia Dwork's work and her colleagues at Penn and so on. And so now we're even seeing companies starting to use differential privacy for certain applications. So now it's becoming practical. We have a lot more to do to make it understandable to mere mortals and to scale it up. And then what about the use of cryptographic cryptography? I think that one of the exciting areas that we can see as a security community is making these cryptographic techniques, such as homomorphic encryption and secure multi-party computation, practical in the way that if you have a particular scenario that you want to light up, or if you have a particular problem you want to solve, you don't have to solve the general, but you can solve that problem, or you can actually light up that scenario, and it can go a long way. And this is something that I think is one way for applied cryptography to get into practice. So let me give you one example. This is something that, again, some researchers at Microsoft Research did just this past spring. And this is a beautiful marriage of our cryptography group who built a secure encrypted arithmetic library called SEAL that allows you to build protocols using homomorphic encryption, and the marriage between the cryptography group and the machine learning group. And they applied it to a medical example. And here the idea is that you have your DNA, for instance, or any personal health records that you want to put into the cloud, and you don't want the cloud to read your data, but you want interesting analysis to be done of your, say, your private data. For instance, if I have a disease, I would like it to be compared to some model that's been trained to detect whether I have that disease or not. And so you can imagine a cloud service that analyzes genomic data and does some prediction or at least some classification based on individual DNA. And so, but you want this all secure. And so this is the motivating example. So this is, I think, is a pretty common motivating example. So how can we do this in a practical and secure way? Well, the machine learning people on the team basically said, well, we could use deep learning to do the classification and the training and so on, and this is all fine and dandy. And what's interesting about, in particular, this deep learning method is that, yes, we use these sigmoid functions and blah, 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 and the cryptography people will say, well, we don't actually know how to make those functions homomorphically, we can't apply homomorphic encryption so easily to those functions. But this is where the marriage between cryptography and machine learning come together, because what the SEAL library can do is basically let you compute over polynomials really quickly. And so what is the simplest, and so in these machine learning algorithms, it's not so much that it has to be a sigmoid or these fancy functions. What's important is that it has to be nonlinear. And so this is the aha. What is the simplest nonlinear function? Well, let's say, I'll give you a hint. What is the simplest nonlinear polynomial that you could use? And, it was once that aha, once the cryptographers and the machine learning people realized, oh, I have a toolbox for you, and this toolbox works in a way that you wouldn't imagine, and you put them together, then the lights go on. And so we were able to use this secure encrypted arithmetic library to build these machine learning algorithms, and they perform quite well. So this is a canonical image set, these optical character recognition numbers from MNIST, and we can do predictions in 5 minutes. The reason we can do 4,096 predictions in 5 minutes is because of the highly parallel nature of how you actually are computing over the polynomials. And we did a pneumonia risk predictor on medical records. Again, this is fast enough. And if it's your DNA, you'd be willing to wait 40 seconds or 2 seconds. So this is state of the art. These are 3 granted demo applications, but it goes to show what is possible. And we released the SEAL library to the public last November, so I encourage all of you who are interested to go ahead and do your research projects using this library. Okay, one last challenge I wanted to pose to all of you in the audience is, how can mutually distrusting parties share data sets to benefit from their union? And so here's the setup. You've got lots of different hospitals. Each hospital has certain patient data. And you know that if you can combine all the patient data from all the hospitals, the way I like to put it is you can build the uber machine learning model that can do this classification based on some disease or not. But the hospitals don't want each other to see each other's patient data. So we want to do this, build this uber model, let's say in the cloud, and we want to do it in a way that the hospitals can't see each other's data. So again, we can appeal to either using applied crypto, for instance, secure multi-party computation, or hardware approaches like Intel SGX enclaves. And so this again is once I say this, I think all of you can run home and go figure out how to do this. But this is state of the art. This is where we can potentially be going. And this is what I mean by providing technology solutions to what today is done in terms of policy and rules and regulation with respect to promising and ensuring privacy to customers. There's an interesting twist on this, which is I've always said to the people, okay, yeah, I can build this uber machine learning model, but then I can also build a machine learning model per hospital, and then I can do what I would essentially call a diff between the uber model and my model, and then maybe figure out some information about the other patient data. And that seems like a violation of what I'm trying to achieve. And so the way to address that is to actually throw in differential privacy in terms of returning the results. So it all comes together, but we as a community really have to work hard to make these technologies practical and scalable. But if we can, then we can do so much. Okay, so I'm going to stop there. And just summarize, I've been talking about cyber-physical systems, but of course I've also been talking about it with the lens of CyberTrust, reliability, security, and privacy. So, thank you very much. We have time for questions. Hi, Brian.
Hi, Rick Farrow. I think it's really nice that you're going to do rewrites of a lot of the basic parts of the internet protocols, although some of those protocols are Turing complete, so there's no way you can ever prove that they're actually the parsers are secure. But I think what's way more important, I just looked it up, there are 11 million professional programmers in the world today, and obviously most of them are not in this room. Okay, most of them do not even belong to ACM, they're not professors. What we find are examples like what we saw in the failure of telematics last year, the Ian Foster paper at Woot, where they found a telematics device that had the telnet port open, and it was mapped to an IP address. You could also update this device over the internet. They had installed the private key of the SSH key pair on the device. Now this is because the people who are programming don't understand security. They get a toolkit, they use the toolkit to the best of their ability, and they do things like leave in the debugging ports. So what I think we really need are tools that make building secure devices brain dead simple. So by default, when you're finished building this device, it doesn't have these dangling things hanging off that make them easier to hack. So this is one of the things I'd suggest people would think about when they're thinking about building a secure internet. Comments?
I'd like to comment on that. Thank you for that comment and question. I do think that, especially for the faculty in the audience, it is our responsibility as we're teaching software engineering and programming and computing and operating systems, whatever, when we're teaching computer science to our students, we do need to have them have security in their mind. It's not an add-on. It's not something you think about after the fact. It's something that it's part of defensive programming, whatever you want to call it. So I do hope that more and more relevant courses are being developed and taught, or at least in some of the courses where it's like networking or operating systems, that it's part of the course curricula. Because first of all, it is we who are teaching the next generation, programmers, and also companies are looking for that expertise coming out of undergraduate and master's programs.
Thank you.
Brian.
Hi. Brian Ford, EPFL. Enjoyed your talk. You alluded a couple times to what I perceive as kind of a coming Cold War, mini Cold War in the security community between the two very different philosophies of data protection. There, between the kind of fancy crypto side versus the just trust intel side, approach, right? Yeah, there's a lot of things you can do with fancy, difficult, heavyweight, crypto of various kinds, but you can also achieve the same thing just with SGX and can you comment more on that? Kind of predict. Do you have positions to state? Or, what do you think the preferred or less preferred outcome of this possible upcoming war might be? Or
First
am I
of all,
just?
I don't think there's a war.
Okay.
I think we as scientists and engineers, technologists, really should be using our entire arsenal to fight the real war, which is the bad guys in the security world. And we shouldn't be fighting each other for sure. I think we can be, I think some of it is a matter of timing. Some of it is a matter of application. So I think that, let me just state a little clearer. In terms of hardware-like approaches like SGXs and so on, I think there's a lot of promise there. And if we do eventually see widespread deployment of those kinds of processors, it's going to, quote, I hate using this trite term, light up a lot of scenarios that we would love to see. That doesn't mean that it's going to solve the security problem, because you're still running code in that enclave, and in the end, you should be verifying that code, right? So there's still that verification problem. There's still questions of side channel attacks, and all sorts of security issues that this community likes to think about. So it's not the be-all and end-all. But I think we need to make progress using hardware approaches and seeing what we can do, both from a definitive security point of view, but also from a practical, scalable point of view. At the same time, we are already, and I think I'm quite impressed with how far applied crypto has come to be actually practical and scalable. And I think we should stop this meme of cryptography is expensive, or we can't possibly, when people say the word cryptography, say you shouldn't be running away thinking, oh God, it's never going to perform well. Rather, we should say, what can we do with the crypto we know that can perform well? Because you can actually do quite a lot. And so rather than, again, trying to solve the whole problem, let's take what we know can work and see what interesting problems we can solve with what we know can work. So what I do see happening is, parallel threads with advances in both deployment and, exploration of hardware approaches, with emboldening and confidence building of the applied crypto community, saying, oh, we can do that. Wow, what else can we do? And the performance isn't that bad, So I think this is a great time, actually, to be doing privacy-related crypto and so on. So anyway, does that help? I don't think, I'm just not a war person. I don't think we should be thinking about fighting each other. Stefan?
Hi, Jeannette. So one of the things I think is really interesting about the cyber-physical realm is that you need to touch the real world. And as you alluded in the earlier part, you start dealing with things like probabilities. Because you don't know, in real world there's going to be updrafts, and so your drone is going to be moving up and your control law is subject to all kinds of other things. What that changes, though, is that instead of the kind of binary propositions that we're used to checking in traditional formal methods, is that we're now doing something which is much more akin to saying, is this a scenario that we're in? And that slop leaves open the door for all kinds of mischief, in the same way that, for example, in basketball, it opens up the door for point shaving, right? It is plausible that they beat the point spread but still won. And you can only look at a large number of events statistically and say, yeah, there's probably point shaving going on in the NCAA. We know it. We can't say which shot was malicious, but we know that it's happening. How do you envision us dealing with those kinds of challenges and being able to reason about what collections of plausibly okay things happening together could do that's bad? Because we don't have any corollary. We're used to having these hard and fast binary propositions. Either it's safe or it's not safe. And all of a sudden we're in this world of, it's between here and here, and collections of things are between here and here, and then something happens.
Yeah, this is really this is the heart of the issue in terms of where the technology is going. If we're, for instance, writing probabilistic programs, and probabilities are inherent to, the program is correct with to some degree of probability, we no longer have these definitives it's correct absolutely with respect to some formal specification. And similarly or analogously, a lot of the smarts that we're putting into these systems are based on machine learning algorithms that themselves are statistically, defined in terms of. So all of a sudden, our whole world becomes very approximate and very epsilon, and and we don't even know how to prove things securely or safely in an absolute way in a scalable manner. So yes, we're opening up lots and lots more room for error. And so that doesn't mean we should not do anything, though. I think we as a community need to acknowledge this and then work hard to see where can we reduce the sources of error, or where can we build tools and systems and logics and models to give us more confidence in the software and the algorithms that we're implementing in software in the cyber-physical systems. And we're not going to get this all right all at once in the very beginning. We will learn over time, much as other engineering disciplines have learned over time. But now that we are really dealing with systems that truly can be a life or death situation for us in our self-driving car, whatever it is, it's no longer, oh, well, a blue screen of death, so I'll just reboot. It's serious stuff. So I don't have an easy answer, but I acknowledge what you're saying. It's very, very important. Yes?
Hi, I'm Bill Cheswick. I love a couple of the points you made. The probabilistic one, as a drone owner who has run into some trees, and you had a picture of a drone that ran into a bush, I would love to have it know that if you're above 150 feet above ground, there are no trees, and so it's safer, and so on. I love including that sort of data and can imagine quite a bit. In fact, your demo seemed to have a grassy area surrounded by trees, and that's exactly where it should work. I also love the idea of proving something secure from the silicon atoms all the way up to HTTPS. But I did want to make one point. It is true that a lot of our sensors are going to be low power, maybe a moisture sensor in a cornfield. But you gave thermostats and light bulbs as being power restricted. If your light bulb is using too much CPU power to handle, it has too much power for that, given that micro SD cards now have substantial CPUs on a chip, you might want to pick different examples of low power use. That's all.
Yeah, thanks.
Hi, I'm Len Hawes, U.S. Department of State. There's a considerable, obviously, amount of talk, not only within the research community about, the topics you brought up, but an equally, if not larger, amount of discussion in the policy and governmental community. And a lot of these are being forced into action because of events and other things going on in a myriad of countries and a myriad of sectors. And I'm still feeling that there's a fairly significant disconnect in the amount of sharing of information between these communities. And how do you approach, what's the effort that you're putting forward to saying, how do we get this information and your work, obviously, along with some of the other really great works going on, into the policy and discussions so that there's not just fundamentally, a disconnect or actions being taken that are fundamentally incompatible with what you see as the end results?
So let me speak to that very optimistically. I'm just an optimist anyway. Two concrete examples. Very recently, in the past couple of months, the White House, through OSTP, has convened a series of workshops specifically looking at AI and the implications of AI. But one of the workshops that was probably the most technical was one called Safe AI. And I attended it. I actually gave a snippet of my talk at that workshop, partly because they do see that AI, machine learning and so on, is going to be everywhere, like self-driving cars. And there is a concern that we, like Stefan was saying, there's a lot more room for error now. And what is the government going to do about that? Should there be regulations and usual? And so that workshop was really meant to educate the government, and there were people from the Department of Transportation there, for instance, on technically what is possible today and where the technology community is going. I think one of the most interesting insights I gained, not being an AI person from that workshop, was I think many of you probably know this, those of you who are working in deep learning, for instance, that there's no explanatory power the machine learning algorithm spits out an answer and one can't explain why the answer is what it is. And so that is something that, of course, we in software engineering know has always been an issue. When you find a bug, you want to know what's the cause of that bug and how can you trace back through a piece of software to explain where that bug came from. So there's a whole interest in the AI community for being able to explain the answers. So to get to your question, though, the point is at least the White House and OSTP and other federal agencies in the United States are being educated through talking with the academic and research community. It's a first step, but it's a good first step, and it's a recognition. Within Microsoft, for instance, I hinted at this before. One of the things that I've been trying to do is to talk to our legal and policy people who do set privacy policies for the company and for promises to the customers, to try to educate them by saying, well, here are certain technologies that we can actually build and deploy and use that can actually relax certain stringent privacy policies, or to use that trite phrase again, light up new scenarios. So part of my job where I sit is actually educating our counterparts in policy and legal. It does take a community effort. Now, I think what's very interesting is what you were talking about in terms of cross-nation and cross-government, because people like us in the research and academic community tend to not have a voice at that table to say, hey, it is actually possible for, say, governments to share certain kinds of information with each other in a privacy-preserving manner, or something like that. So that I don't know if. I think I would have to rely on the people who are currently in government agencies, like NIDRD is probably a good example, where people are placed to then talk to the U.S. Part of that conversation. Oh, and then there's DARPA, of course.
Hi, Drew Ding, Qualcomm Research.
Yeah.
Nice talk, thank you. So a question I want to ask is on the formal methods side. It seems to me that many things that we take to be invariants are, in the real world, maybe I can call them almost invariants. With a drone or perhaps some future passenger plane, don't do a maneuver which would crack the airframe. is something that we might intuitively think of as an invariant, right?
Don't what?
Don't pull some maneuver that's going to cause the airframe to crack, right? That would be an invariant. Except occasionally you want to violate that, right? In the sense that if you're in a dive and catastrophe is inevitable if you don't pull out of the dive, which may cause the airframe to crack, it's sort of like there's inevitable catastrophe if I don't do something. This seems like something that I don't know that we have the techniques to reason about. I mean, another example of this is the Hudson River is not generally recommended as a place to land a passenger plane, although that was actually, insofar as 100+ people were saved, that was a good decision to make. So how do you see us dealing with that?
This is a really interesting question/dilemma. I remember when there was the, I think it was that little German wings plane that flew into the mountain or something.
Yeah.
And all of us in the technical community said, well, we could have programmed the thing to say, if you're this close to the mountain, don't crash into it, right? And don't let the human override that. But for any case like where you don't want to let the human control it, you have cases like the Hudson River where, by golly, thank God that that human was in control and had the savvy to land the plane on the Hudson River. So first of all, I think that's an interesting dilemma. In terms of formalizing, what you ask is a very interesting. What you suggested is a very interesting concept of an almost invariant. So this is a new concept. Maybe it makes sense, much like we have approximate correctness, to understand what an almost invariant is. Because what I would say immediately is you need to define clearly the space of that almost, so that it's invariant with respect to, this state space, but not that.
Right.
And once you cross the line, then all bets are off.
Right. My thinking out loud suggestion is that you could somehow formally reason that catastrophe is inevitable. And I realize that needs to be formalized as well, and I leave that to people smarter than I.
Well, the other thing is, of course, even in the usual engineering community, we talk about like 5 nines or 3 nines or whatnot. So people who build real systems, engineered physical systems, understand that it's not 100%. Something is going to fail. But what is my tolerance for an error? What is that reliability 9 that I'm shooting for? We don't have, in software, we still don't think about it. In software, we don't think about that. And certainly in the kinds of algorithms that we're deploying to make our devices smarter, like machine learning and AI algorithms and so on, we're not thinking about that.
Thank you.
So you also talked about Project Everest, which is a very interesting but also very challenging project. For some of the building blocks, I can see that they are small enough that we can start from scratch. Like this MyTLS work that's coming out. So there are certain building blocks where we can basically start and learn or use the lessons learned in the last 20 or 30 years. On the other hand, in this HTTP ecosystem, there are also very complex programs like WebKit or Edge, which are tens of millions of lines of code. So can you elaborate a bit on how you think we can secure those large building blocks in this HTTP ecosystem, such that within the next few years we have a built-in replacement in order to actually prove that I can safely and securely browse the web? Or are there challenges that are likely not feasible in this rather short term?
So you're talking about my big block diagram,
Yes,
right?
yeah.
And you're saying
Yeah, so some of these building blocks are rather small. There we can probably start from scratch. But we also have lots of legacy code. So millions of lines of legacy code. What do we do with this?
So Cedric, do you want to actually answer that question? I mean, we have the expert here, and I don't want to say anything wrong.
Yes, thanks. So, so just first of all, a clarification. So, the scope of the Everest project is to verify everything from the HTTPS API down to hardware or cryptographic assumptions. So, the scope of the project does not include verifying a web browser, for example, which would be the application on top of HTTPS. So, so we want to take HTTPS as an API and implement it securely, and then still get best effort security for applications on top of HTTPS. So now it means that for legacy system, we won't be able to get full formal verification. However, for well-defined subsystems, like if you want to do e-voting, or if you want to do basic functionalities like signing or well-defined sub-application, then for those we can use our secure API and do the extra mile of verifying the application fully and get strong security out of it. But I don't think it will be for every application built on top of HTTPS. It will be for selected, simple, well-defined applications on top of it, for which we have a clear specification to begin with. So no miracles there.
Thank you.
Hi, Deborah Shand, currently at the National Science Foundation. I wonder how you imagine some of these systems will address sort of evolution of how people interact with them over time. And, you know, in terms of the rules that are used for reliability, security, anything else. And I'm thinking of the following scenario. I'm from Los Angeles, and in that area, I do not jaywalk. You know, I would risk life and limb, absolutely. I'm living in the Washington, D.C. area now, in an area where there's a proliferation of stoplights at very small intersections. And within an afternoon, I discovered why it is that there's this entire disregard by pedestrians for any of the lights in this area. And within just a few hours, I became a habitual jaywalker myself. So I can only imagine that when we have systems like, for example, self-driving cars, humans will begin to game the system. They'll begin to understand how the cars behave in terms of preserving the lives of pedestrians, and humans are going to start interacting differently with those vehicles, possibly to negative effect for everybody involved. How do you imagine that our systems can start, you know, evolving, co-evolving with the human behaviors that are almost certainly, you know, given my range of law breaking now, will start to emerge. I hate to admit that here, but anyway, just wondering.
Well, first of all, I have to tell you my LA jaywalking story. So I went to school in Boston, where I don't think there are laws about traffic and pedestrians. And then I moved to Los Angeles after I graduated from school, and I was walking my bicycle literally, I think, you know, maybe 10 feet away from the crosswalk, but it wasn't in the crosswalk. And this policeman comes up to me, and he was about to write me a ticket and about jaywalking, and I said, but, you know, I just moved here from Boston. And he said, don't they have, you know, rules about jaywalking in Boston? I said, I don't know. So anyway, I talked him out of the ticket, but he's, you know, young lady, you know, you should walk in the crosswalk. But, you know, and then actually when I moved to Washington, D.C., I behaved because, you know, again, Washington, D.C. is not like Pittsburgh, where you just, you know, cross the street whenever you want, or New York, you know, who pays attention to law? So I find myself in D.C., L.A., and Seattle, I behave, you know. The light says red, and I wait there, and there are no cars, I wait there. Anyway, I think what you ask is actually a broader question in terms of not just cyberphysical systems, but where our software systems are going for the future. And I now appeal again to a lot of what I see happening in our technology, which is going to be very AI-based. There are going to be a lot of systems that we interact with that actually try to understand our behavior and interact with us as people. I'm thinking, for instance, very, very simply, a lot of the quote, personal assistants and conversational agents that we interact with, you know, the Alexa that you might have on in your home, or the Cortana and Siri that you talk to on your phone, they are learning and adapting to you as a person, and to make these systems more interesting and more personal, they have to understand what it means to engage with individuals, engage with people, and interact with them. So, for instance, we have in the building that I work in, we have these little teeny weeny robots that sit outside the elevator doors. And when you exit the elevator, if you come up close to the robot, you can ask, you know, where's Jeannette's office? And the robot will look at you and talk to you and give you directions. But if you don't come up to it close enough, like what I don't go up to it every day, but you just go by it, it's this little robot. It goes like this. It knows how much to engage with you as an individual. So we are building systems that understand human behavior at that level of when to engage, who to engage with if there are multiple people, you know, standing around the robot. And it's pretty remarkable that we can build these systems that can be so interactive. And I don't just mean HCI kind of interactive. I mean really understand when is the human trying to get my attention as a robot? And how do I get the human's attention in order to engage with it? So we're seeing more and more systems that have to understand fundamentally human behavior in that way. And then I think we need to think about it not just as an individual, but in terms of societal, social norms and societal behavior. So there's a lot more that we need to do. And this is why when I was at the National Science Foundation, I started these programs that were crossed between SCIES and the Social and Behavioral Economics Science, the SBE Directorate, because I saw that computing was, whether it was, you know, CyberTrust or social and computational systems or economics and computer science, I saw that computing was really abutting and going into these other areas and needed the social sciences, the behavioral sciences, scientists and the economists to work with the computer scientists to kind of figure out what was going on. So I just see more of that happening.
Thank you.
Okay, let's thank our speakers.
Thank you.